So I want to talk about how broadcasting can cause problems when we're doing ordinary least squares regression with linear algebra in numpy using Python. All right, so let's import numpy and let's see what we're after here. I've created a matrix X, which is 100 by 3, and I've created a vector of parameters, which is a one-dimensional array and equal to 1, 2, 3. Then I've created a vector of error terms, which is also one-dimensional with length or size equal to 100. And finally, we have our outcome y, which is 100-dimensional. All right. To understand why broadcasting can cause problems here, let's try to see what happens if we make a minor change. We just change our error term so that instead of being a simple 100 list of dimension 1, it is now 100 by 1, so it's a two-dimensional array now. What this means is that our x beta, the predicted value, is a one-dimensional array, and it's 100 long, and so we're adding this one-dimensional array to a two-dimensional array, and the way that numpy interprets this is that it thinks, these two matrices, or these two variables here, x beta and u, they don't conform, they don't have the same number of dimensions. How should I extend the dimensions of this one-dimensional array to conform to that of this two-dimensional array? And the way that it's doing it is that it's creating all possible combinations of sums of this one-dimensional vector and this two-dimensional vector. And that's not what we intended. We can in fact remedy the situation by also making beta two-dimensional. Now beta has two dimensions. It's a column vector, and what that implies is that x times beta here is now also two-dimensional. It's 100 by 1. So now what we're doing here is we're adding two-dimensional arrays, and so the result is that our outcome y has the expected dimensions. And let's just print it out, and let's go back and make sure that we're actually getting the same result now that y is simply one-dimensional. Let's just take the first 10 elements. Of course it's not the same because we're not seeding our random number generator. Important thing to remember. Always seed your random number generator, or otherwise you're going to get different answers when you run it multiple times. Alright, so let's do it once more. Make beta two-dimensional. You can see that y is now two-dimensional also, and the first 10 elements here, 2.0501862, that's the same, and this one ends with 8408, that's also the same. So we're getting the same answer, but it's just if one of these two is one-dimensional and the other is two-dimensional, then we're instead getting all possible combinations of sums for those two vectors. Which actually means that, as you can see, along the diagonal, we're getting the sums of the first element from one and the first element from the other, the second element and the second element. So actually, if we were to type, sort of take out the diagonal, and let's just print out the first 10 numbers here, then we're in fact back to the same situation where we're getting the correct numbers there in the diagonal. But of course, we don't want to do this because we're creating an n by n matrix, which is ginormous and takes too much computing power. So in short, take care, kids. Make absolutely certain that the number of dimensions on your parameter vector is equal to the number of dimensions on your error term, or if you, on the other hand, if you're evaluating, say, a likelihood function, then typically what you're doing is you're computing a residual, which is going to be y minus x times beta, and we then, yeah, that's our residual, and typically our log likelihood function is something like something relating to the negative of the sum of residual squared. And so this likelihood function turns out to be a, well, I guess actually we can't see what's going on underneath here. So let's print out the full vector of likelihoods. And this one is then 100 by 100. So if we just type sum up here, it's actually just going to sum all 100 times 100, so all 10,000 elements of LL. So this could be hiding a very nasty bug inside that simply is due to the fact that in that calculation, let's make it a little bit more realistic again. We go back to a situation where y is one-dimensional and beta was one-dimensional when we were creating it, but now let's suppose that it has somehow become reshaped and has become two-dimensional. Then the same problem occurs because we're subtracting the one-dimensional vector y. From it, we're subtracting this two-dimensional vector x beta. And that is how broadcasting can really mess us up when we're doing ordinary least squares, or in general when we're doing econometrics with matrices and vectors in numpy.